Today we want to look at some average values again. Remember, we're thinking of average values. We're thinking of averages the same way we always think about averages. We add everything up and divide by the number of things. It gets a little bit weird because adding everything up, we're trying to add up over a continuum. We've got that. That's what definite integrals are all about. Then we'll divide by the number of things. That's a little bit tricky, but we'll just take the length of the interval as the number of things. Thinking in terms of an average as a density. How much is there divided by how much space it's taking up. So in this problem, we're also combining this with our approximating definite integrals. We'll combine this with the work we had with approximating definite integrals. So the information that we have is sparse. So we'll use an approximation technique to find the definite integral from 0 to 12. And then we'll look at some variations on this problem. Now, in particular, we want to note that I want the average value of the function, not the average of the values that we know. We want the average value of the function, not the average of the values that we know. What we want to notice about this function is that this function is quadratic. Notice that the rate of change is not constant. So first we subtract 10, and then we subtract 20, and then we subtract 30, and then we subtracted 40. So the rate of change is not constant, but the rate of change of the rate of change is constant. So our second derivative is constant, which means our original function is quadratic. So negative 10 minus 10 to minus 20, minus 20 minus 10 is minus 30, minus 30 minus 10 is minus 40. So the rate of change of the rate of change, our second derivative, looks to be constant, which suggests that our original function is quadratic. So if there's this decreasing quadratic function, we can see that the second derivative is negative. So we know that this function is concave down. So we know a lot about this function right away. One thing we do want, it's suggested that the function f is concave down. This is assuming that I'm not pulling some kind of shenanigans and not telling you some vital information about what's going on in this function. If we encountered this type of number setup, we would say it looks like we're dealing with a decreasing concave down quadratic function. But we do want to notice that with these second derivatives being all negative, that suggests the function is concave down. That's going to change how our approximations go. All right, so we want to find the average value of f of x on the interval from 0 to 12. So we're going to take the integral from the definite integral from 0 to 12 of f of x dx. That's us adding up all the values. And then we'll divide by the amount of space that it takes up. So divide by the length of the interval. And so we don't have to write our definite integral as a top part of a fraction. We'll write the 1 over 12 out in front. Now, in this case, we need to approximate the definite integral from 0 to 12 of f of x dx. We have a lot of ways to do this. Our most accurate one is going to be Simpson's rule, which we can do because we can calculate midpoints. And it will go quickly because we can only make 2 rectangles. So I'm going to integrate from with n equals 2. And so a delta x of 6. And we'll approximate our definite integral with Simpson's rule. So I need the mid-2 approximation. So mid-2 is going to be delta x times the two midpoints, 90 and 40. Then we'll realize I don't think I can multiply these without mechanical assistance. So 90 and 40 times 6 is 780. And we'll need a trapezoidal rule. And since I have not calculated left and right approximations, I'll just do the trapezoidal rule directly. It's still only two rectangles. I'll take my delta x, divide by 2 because it's the average of the left and right. 100 appears one time, 70 appears twice, and the 0 appears one time. So I'll have 240 times 3. Oops. 720. So if we want to average these two with Simpson's rule, I'll take 2 midpoint rules and 1 trapezoidal rule. So Simpson's rule is going to be the average of 2 midpoint rules and 1 trapezoidal rule. $760. With the given information, this is our best approximation of the definite integral from 0 to 12 of f of x to x. Now, if I want the average value, I just take my definite integral, which is 760, and divide by 12. $63 1/3. A few of the other things that we want to observe here, just to make as many connections as possible. On a test, we're done with this problem. We've got 63.3. We put a box around it. We double check that I said round to 3 significant figures or round to the nearest tenth, so we don't miss points for that reason. And then we move on because that's all we would need for the test. But let's think about how these things are connected to other things that we recognize. We had observed that the function looks quadratic because our second derivative, that second row of differences, seems to be constant, which suggests that the function is quadratic. All those second derivative values are also negative. That tells us that the function is concave down. So that's another thing that we want to notice. Here we see that the function is decreasing. This row here says that f of x is decreasing. And these negative tens suggest that f of x is concave down. Since we know that f of x is concave down, that suggests that the trapezoidal rule connecting these points with a line is going to be an underestimate. And it looks to be the case because our trapezoidal rule was less than our midpoint rule. So f of x is concave down suggests trapezoidal rule is an underestimate. The trapezoidal rule is an underestimate for concave down functions. Let's think about that geometrically. If we think about that geometrically, if we have a function that is decreasing or increasing, well, let's draw a function that is concave down. And if I connect those points, the endpoints, with just a line like we do in the trapezoidal rule, we can see that we're going to have an underestimate of the area. That space is an underestimate. The assumption in a trapezoidal approximation is that we have a linear function. So if I connect those points with a line, then we can see we have an underestimate. There's area that we want that is missing. And it doesn't matter if the function is increasing or decreasing. Here's a function that's increasing in concave down. If I connect the endpoints with a line like we do in the trapezoidal rule, we can see that there is area that is missing. That area is not in the trapezoid, but it is under the curve. The trapezoidal rule is an underestimate on a concave down function. These are all things that are important to keep in mind because they'll show up. If we keep these things in mind, if I calculate my trapezoidal rule at 720 and I calculate my midpoint rule at less than 720, we know that something has gone wrong. You know, the trapezoidal rule for a concave down function should be an underestimate. So either our trapezoidal rule is too high or our midpoint rule is too low. So that would cause us to go back and check our work, even though the answers to the odd numbered exercises are not in the back of the book. Is that even a thing anymore? It used to be that in math textbook, the answers to the odd numbered exercises were in the back of the book. But now we're kind of getting away from physical books. And so like Wiley Plus just has the odd numbered exercises where you click on answer and it shows up right underneath. So a little bit more efficient, but we couldn't do that with a physical hard copy of a book that's printed on paper. So notice that if we just average the scores, that's not what we want. What is the average of these scores? I got a 10, a 9, a 7, and a 4. So the average of the scores is 60. So the average of the scores that we have, the data that we have, that's just a 60. But this is a weighted average, and the weights show up in the concavity. Notice that our actual, or our best estimate for the average value of the function was more than the average of the scores. That suggests that the higher scores are weighted more. So the question is, should the higher scores be weighted more? Well, let's connect that to the stuff that we've observed. Yes, the higher scores should be weighted more because the function is concave down. So there's another observation that we want to make. The higher scores are weighted more because the function is concave down. So this is another aspect of the concave down part of the function. Whether the function is increasing or decreasing, the higher scores are weighted more. Any questions? Is that okay? A similar thing happens with the midpoint rule. We'll see that the midpoint rule for a concave down function will always be an overestimate. So here I'm going to draw a function that's concave down. Then I'm going to draw the midpoint rule approximation. I used red before, so I'm going to use red again. So here's our function being concave down. Since the function is concave down, there's going to be more decrease after the midpoint than there is before the midpoint. So because the function is concave down, there's more decrease after the midpoint. So here, that area, the green area, is going to be more than, what color should I use? I use purple. For a concave down function, we'll have less area before the midpoint, more area after the midpoint. Before the midpoint is where we are missing some values. After the midpoint is where we are keeping more the values. So we have more here that we're keeping, that area after, that's in our rectangle, but not under our function. So the green part is overestimate. And the overestimate outweighs the underestimate. So the over-under for the midpoint rule and the trapezoidal rule are dependent upon the concavity of the function. Any questions? We can draw a similar picture for a concave up, concave down increasing function. So incidentally, if you want to draw something concave down and demonstrate the midpoint rule, just find the middle, connect it with a line, and then push the midpoint up to make things concave down. Just there. Or if you really want to exaggerate it, there. And now we have to make it concave down. That straight line would be the trapezoidal rule. So if we push up, we're going to get some underestimate from the trapezoidal rule. Here we have a concave down function again. Now, since the function is increasing, the over and under change places, but there's more area before. And this area is, oh wait, no, they don't change places. I don't know what I was thinking of. I was thinking of left and right. There's some overestimate, some stuff in our rectangle that's not under the function. And here's our underestimate. In this case, we see more area before the midpoint, less area after the midpoint. What we really want to be looking at is the over and the under. Any questions? Now, we should be complete about this and show that it reverses for a concave up function. There. See, oh, if it's concave up, it's just the opposite. Multiply by -1. That's the other reason that I do this, for this one specific example, because I can't do that with the boards. It's hard times back when I taught this class on the whiteboards, because I couldn't just flip them over. Any questions? So sometimes the question comes up, how far off is our approximation? And we don't really have a way of figuring that out unless we had more data. If we had more data, then we could just make a better approximation to begin with. If we actually knew what the function looked like, then we could actually calculate it. I do always build a quadratic function, mainly so I could point out this concave up, concave down stuff. So you could, if you would like, figure out what quadratic function hits all these points, and then integrate it from 0 to 12 to see how accurate our Simpson's rule was, despite the fact that I only had 2 rectangles in this average. So that might be an interesting question. Can we find a quadratic function that fits this description? We'd have to figure out what A, B, and C are. I could see one of them right away. What's the leading coefficient? I'll even tell you which one I could see right away. What's the leading coefficient? More importantly, can you tell what question I'm not going to be answering today? Or even this week? So if we're interested to compare this to where I may have got this from, if this is indeed quadratic, then we can figure out what that quadratic is and then just integrate it from 0 to 12. That might raise some questions. How many quadratics would fit this description? Well, we do have 5 pieces of information and we are looking for 3 constants. So perhaps we can. Perhaps it'll just be an approximation. Perhaps I didn't get this from a quadratic at all. Although you know I did, because you saw I just subtracted 10, then 20, then 30, then 40. I suppose I could be a jerk if he's like, well, after 12, it becomes linear. Then I'm just cheating. Any questions? Comments? This I wanted to combine our approximating definite integrals and our thinking about averages, mainly because I care about this part. So when we think about averages, we have to think about the weights that go along with those averages. We can't just find the average of the scores. But what this tells us, since the average here was the average of the numbers that we're looking at, that tells us that there's more weight on the higher numbers. What causes the more weight on the higher numbers? It's the concavity. It's how the function is bent. I'm sorry about that. One of the ways that we could look at this is I could come up with a different function. If we think about this function, it looks like I'm making a linear function because I'm just subtracting 20 the whole time. Oops, this is g of x. We have a constant rate of change. The second derivative is going to be 0. There's no concavity. It's the concavity that determines whether the trapezoidal rule gives us an overestimate or an underestimate. So if the function is linear, the trapezoidal rule is going to be spot on. There's going to be no difference. When we're dealing with a linear function, the trapezoidal rule is going to give us the exact value that we're looking for. If we do a midpoint approximation, we still have a delta x of 6. Because we're doing still two rectangles or 2 trapezoids. And the midpoints are 80 and 40. And the trapezoidal rule will be 6 over 2 because we're finding an average. 100, 2 60s, and 120. Not 120, one copy of 20. Well, the midpoint rule and the trapezoidal rule agree. And so when I stick the actual value in between those two, it says the actual value must be equal to those two. And if we calculate the average value of the function, 720 divided by 12, that gives us 60 right in the middle. But we had a very simple function here, so it was nice and linear. Any questions? How's that, brother? The things that we want to look for when we try to recognize patterns, we start by looking at differences. How are things changing? This is what we naturally do. If I give you a list of numbers and I say, look for a pattern, the first thing you're going to do is you're going to look at differences. Because the first thing that we learn after we learn how to count, the first operation we learn is addition. It's like the oldest thing that we have mathematically in our minds. After we count, after we learn sequential, we learn addition. We learn the sequence of numbers, then we learn how to add numbers. So it's the oldest thing we have. Then we learn about other patterns of multiplication. And now all we're doing is looking for differences and then looking for differences in the differences. We look for differences and then we think, what are the differences again? Any questions? Comments? Slide them up. All right, that's going to do it for today. That's going to do it for this week. I will see you all on Monday. Everyone have a good weekend, and thanks for playing.